Hello, Algebra 1. Today we're going to be doing a little review of quadratic functions. So we're going to be combining sections 9.1 and 9.2. Hopefully you get a chance to work on the Desmos activity. Some of you guys, hopefully you got a chance to work on the Desmos activity. Gave you a chance to kind of see the different types of transformations that would be taking place. It'll definitely help when we go through this worksheet together. So we're going to first start with the parent function f of x equals x squared, which is going to be the parabola whose vertex is at the origin. The way we can graph this function, if you don't remember what f of x equals x squared looks like, is by just plugging in points, right? So we're going to fill out this t-chart here. And so if I plug in -2, for example, I'm really just going to be computing f of -2, which means I'm just replacing x with -2 using this equation right here. And when I make that substitution, I just get -2 squared, which is 4. So that gives me the first point, which is -2, 4. And then I could repeat that, right? I could plug in -1. F of -1 means I just plug -1 in. So I'm going to replace x with -1. And if I simplify, I get +1. That gives me the point -1, 1. If I plug in 0, this one's kind of nice because 0 squared is just 0 times 0, which is 0. That's the origin. I'm going to plug in 1 here. 1 squared is just 1. So I get the point 1, 1. And then lastly, when I plug in 2, I'll get 2 squared, which is 4. And that gives me my fifth point. And then from there, I'm going to draw my curve. You want to make it U-shaped, right? So you want this part right here to be smooth. It should not look like a V. There shouldn't be any sharp corners. And this is the graph of f of x equals x squared. So what we're going to be doing today is we're going to be taking this parent function and we're going to be transforming it to graph functions that are a little more complicated than this. One thing I do want to note is that when you look at these 5 points here, and I want you to look at the vertical distance between consecutive points. So for example, if you notice here, these points are 3 units away. These points are 1 unit apart. Similarly, there's 1 unit apart here, and then 3 units apart here. We're going to be using the structure when we graph these quadratic functions. Now keep in mind though, this is only true because the a value is 1. Right? The coefficient of the x squared term is going to be 1. One thing to note is that that point right there, if you remember, is your vertex. And so a lot of times when I'm graphing these transformations, I'm going to always start by figuring out where the vertex is at. So looking at this next example, I want to graph g of x, which equals x squared minus 1. So if you remember from your Desmos activity, that -1 is going to be a vertical shift. And vertical shifts always tell you the truth. So when I see this -1 at the end, I know that that means I'm going to take the parent function, f of x equals x squared, and I'm going to move it down 1 unit. So what I'm going to do is I'm going to take the vertex, which I know is normally at the origin, 0, 0, and if I move it down 1 unit, this is going to be my vertex. And then from there, I'm going to use the structure again where I know my next point will be 1 unit above it, to the right and to the left of it. And I know that the next point will be 3 units above it, both to the right and to the left. And so when I graph, my curve will look something like this. Again, make sure it looks like a letter U, right? It needs to be smooth. And so now from here, we're going to find some key characteristics of this quadratic function. The vertex is at 0, -1. When we're talking about the zeros, those are going to be the x values that when you plug into the function make it 0. So if you look at the previous example, 0 happens to just be a 0 because when you plug in that number, my output was 0. It was just a coincidence that 0 happened to be a 0. But any number could be a 0, right? As long as when you plug into the function, your output is 0. So in this case, when we talk about zeros graphically, the zeros are where the graph crosses the x-axis. So it crosses it at -1 and it crosses it at +1. And I'm looking at these points right here when I look at the zeros, right? Those are my 2 points, okay? Domain, we're talking about all the possible inputs. In this case, your domain is just all real numbers. No matter what x value I plug in, there's always a point that corresponds to it. And then the range will describe all the y values. So in this case, you notice that all my y values are greater than or equal to -1. If you notice here, -1 is my smallest y value, right, for any point, and all the other y values are greater than or equal to that. Now, another way we can write the range is using interval notation. I can write this as -1 to infinity as well. And I use a bracket because of the fact that it's greater than or equal to, right? -1 is included, okay? Now, for intervals of increasing and decreasing, you always want to remember that you want to read it from left to right, okay? So when you're looking at this graph, you always want to look at it from left to right. So starting from the left and going toward the right, you can see that my graph is decreasing, right? Because it's going down. And then after 0, it's increasing, right? It's going up the hill. You could think of it that way, right? You could think of decreasing as going down the hill, and the increasing is going up the hill. And so when you look at the intervals, we're looking at the x values, right? The x values for which the function is increasing or decreasing. So once again, it's decreasing here. And then after 0, it's increasing. So for intervals of increasing, I can say x is greater than 0 because that's when the function is increasing. Or using interval notation, I can say from 0 to infinity. Here I use parentheses on the 0 because 0 is not included in the interval. Intervals of decreasing would be everything less than 0, which you can write as -infinity to 0. And just so we're clear, let me color this so you can see that, okay? So when I talk about intervals of increasing, I'm looking at this portion of the graph right here. And when I'm looking at intervals of decreasing, I'm looking at this part of the graph, right? Because again, you're always looking at it from left to right. So hopefully you get an idea of how to do that. Let's look at another example together. So here for number 2, we have h of x equals -x² plus 4. So here that negative in the front, if you remember from the Desmos activity, that's a reflection across the x-axis. And then that plus 4 means I'm going to move it up 4 units. And so with this transformation, I want to first reflect it. So when we reflect it, what we're doing is we're taking the graph of this parent function, and we're going to reflect it across the x-axis first. Should look something like this. And then from there, I'm going to move everything up 4 units. So take every single point and just move it up 4 units. And you should end up with something like this. And that's our final answer. That is this graph right here. Now from here, the vertex is, in this case, the highest point, which is 0, 4. The zeros, again, refer to where does it cross the x-axis. So when I talk about the zeros in this case, the graph hits it here and here, which would be at 2 and -2. The domain would be all real numbers. The range, which describes the y values, would be all y values which are less than or equal to 4. Because again, if you look at that graph, every single point here has a y coordinate that's less than or equal to 4. You can also write this as -infinity to 4 with a bracket. Intervals of increasing, always look at it from left to right. So for intervals of increasing, left to right, you notice how this is where the graph is increasing, it's going up the hill. And then when I'm talking about intervals of decreasing, it would be over here. This is where the graph is decreasing. So intervals of increasing is when x is less than 0, which you can write as -infinity to 0 using interval notation. For intervals of decrease, it would be x is greater than 0, which is also written as 0 to infinity. Either one's fine, okay? So hopefully you get an idea of how we can find these key characteristics based on the graph of the quadratic function. Let's look at 2 more examples. So now they start getting even more complicated because now in this case we have 2 transformations that are taking place. So hopefully by now we're able to recognize the fact that this -1 at the end means I move down 1 unit. Whenever you have the number at the end, that's going to correspond to the vertical shift, how many units you move up or down. And the vertical shifts are always truthful. So when I see that -1 at the end, I know I'm just going to move it down 1 unit. Now this -2 that's grouped with the x, that's going to tell me I'm going to move the graph left or right. And with horizontal shifts, they're never going to tell you the truth. So when you see x -2, it's very tempting to say left 2 units, but you want to think the opposite. You're going to move right 2 units. And that's what I mean when I say that horizontal shifts don't tell you the truth. They're not truthful, because -2 makes it seem like you're moving left 2 units, but you're really moving it to the right 2 units. So once again, what we're going to be doing is we're going to be taking this graph here, this graph of f of x equals x squared, and we're going to be shifting it to the right 2 units and then moving it up 1 unit. But typically the way I graph this is I always start with the vertex, because I know that the vertex for this graph right here is at 0, 0. And so taking the vertex, let's just move that. So knowing that the vertex of the parent function is normally at 0, 0, I'm going to take that point and move it right 2 units and move it down 1 unit. And so now my vertex will be there. And then from there, I know that when I graph additional points, I'm going to move up 1 unit, and then I'm going to go up 3 units. And so my graph will look something like this. At this point, what I want you to do is I want you to pause the video so that you can figure out these 6 characteristics. And then when you're ready, I want you to press play to check and see how you did. So for your vertex, you should have gotten 2, -1. Again, the vertex is either your highest point or your lowest point. Sometimes we call it the turning point. For the zeros, you want to look at where does the graph hit the x-axis. So at 1 and at 3. So those are going to be my 2 zeros. The domain is all real numbers. The range will be all the y values that are greater than or equal to -1. In this case, you can also write it as -1 to infinity if you want to use interval notation. Now for intervals of increasing, the graph is increasing on this interval because again, you're looking at it from left to right. And the graph is decreasing along this interval here. So intervals of increase would be x is greater than 2, because if you look at this vertex here, it's at 2, -1. So everything greater than 2 is when the graph is increasing, or 2 to infinity, which means the graph is decreasing when x is less than 2, which you can write as -infinity to 2. So hopefully you're able to get that correct. If you made any mistakes, make sure you understand what we mean by domain and range, zeros and the vertex, as well as intervals of increase and intervals of decrease. So let's look at number 4 together. This is the final problem. So for number 4 here, we have 3 things going on now. We have this negative here, which tells me this is going to be a reflection across the x-axis. Then I see this -1, which tells me this is a horizontal shift, and horizontal shifts never tell you the truth. So when I see a -1 there, I'm really thinking in my head, okay, right 1 unit. And then lastly, that +1, I know that's going to be a vertical shift, which always tells you the truth. So I know that means I'm just going to move up 1 unit. Because a +1, typically you think up 1. So what we're going to do is we're going to graph this parent function. So the first thing I'm going to do is I'm going to take f of x equals x squared and reflect over the x-axis. In which case my graph will look something like this. All I'm doing is I'm taking that parent function that we graphed at the very beginning. And then from there, I want to do my translations, where I'm going to shift it right 1 unit and then up 1 unit. So if I do that, I'm going to just take the vertex and shift it right 1, up 1. This would be my vertex. I'm going to do that with each of the points. And in the end, you'll end up with something like this. So this red curve is the graph that we're trying to find. That's the graph of f of x. At this point, let's find all the key characteristics. I would recommend you pause the video and try it again on your own. And when you're ready, press play to see how you did. So for the vertex, you should have got 1, 1, which in this case would be the highest point. The zeros correspond to where does the graph cross the x-axis? At 0 and at 2, I believe. So those would be my zeros, 0 and 2. Your domain is always all real numbers when it comes to quadratic functions, because you can plug in whatever value you want for x and you'll always get a y value out of it. The range in this case is everything less than or equal to 1, which you can also write as -infinity to 1 with a bracket because 1 is included. Now when we talk about intervals of increasing, again you want to make sure you look at it from left to right. Here's where my graph is increasing. And the intervals of decreasing will be everything after my vertex. So if you notice my vertex is at 1, 1, we're looking at the x values for which the graph is increasing. So we can say my graph is increasing when x is less than 1. Right, that's on the left side of the vertex, which you can also write as negative infinity to 1. And then my graph is increasing when x is greater than 1, which you can also write as 1 to infinity. So make sure you guys understand the various transformations. All we're doing at the end of the day is we're taking this parent function, which is f of x equals x squared, and we're moving it around, we're reflecting it, and we're translating it. So make sure you understand these concepts, practice. If you have any questions, please let me know. Alright guys, this is the end of our review of quadratics. I hope you guys have a wonderful rest of your day.